If anyone can generate perfect fakes, how do you ever prove what's real 5 years from now? In this course, you'll see how to design blockchain-based architectures that make data, actions, and AI outputs cryptographically verifiable, even under advanced AI threats and future quantum attacks. For most of computing history, we simply trusted servers, admins, and logs to tell the truth. That model is breaking. I can forge content, tamper with models, and poison data at scale, while a single privileged account can silently rewrite history. In this world, seeing is not enough. We need trust that can be independently, cryptographically verified. Verifiable trust ultimately comes down to the calculus of value, scarcity plus provenance. Scarcity means something is limited or uniquely identifiable. Provenance means we can prove where it came from and how it changed over time. Combine both, and you get a reliable chain of custody that makes digital assets genuinely trustworthy. The first fundamental pattern is the digital fingerprint. We run any document or file through a hash function, such as SHE256, and it outputs a short fixed-length value that uniquely represents that content. Even a 1-bit change produces a totally different hash. Architecturally, we store only the hash on-chain and keep the full data off-chain. Anchoring in time is about proving that some data existed no later than a specific block height. You hash the data, store only that hash in a transaction, and let it be included in a block. From then on, anyone can recompute the hash and check that it appears in that historical block. As more blocks are built on top, rewriting that point in history becomes exponentially harder, turning your hash into a durable, time-stamped proof of existence. The signed statement pattern turns important events into verifiable claims. Something happens. A signer creates a statement describing it, and then signs that statement with a private key. The signature proves who made the claim and that it wasn't altered. Finally, we anchor a hash of that attestation on-chain, giving it a permanent, time-stamped reference. At the identity layer, everything starts from who or what is acting, and which key they control. In classical PKI, a certificate authority vouches that a given public key belongs to a legal entity. With decentralized identifiers, the user anchors their identifier and associated DID document on-chain, without a central registry. We can further bind that identity into hardware using TPMs or secure enclaves to prove that a particular device or sensor is genuine. Privacy-preserving provenance solves a tension. You want the world to verify authenticity, but you don't want to expose raw data or trade secrets. Hash-only commitments let you prove this exact asset existed at this time by publishing only its hash. Salting protects against brute force guessing of the original content. On top of that, selective disclosure lets you reveal decryption keys or full payloads only to designated auditors, while everyone else sees just the public, immutable anchor. Zero-knowledge proofs let you convince someone a statement is true without exposing the data behind it. Think of saying, this model was trained only on licensed data, while never revealing the dataset itself. The verifier trusts the claim because the math makes lying extremely hard, yet no raw data, features, or exact records ever leave the prover's side. A provenance registry separates storage concerns from trust concerns. All the heavy assets, models, and datasets live off-chain in IPFS or a cloud store. On-chain, you only keep compact fingerprints, an asset ID mapped to its hash, signer, and timestamp. Verification is simple. Fetch the asset, recompute the hash, and compare it with the registry entry. This keeps costs low while the smart contract enforces governance over who's allowed to create or update attestations. Now let's look at the read side of trust, how a client convinces itself a file is legit. The client computes a hash of the file, then asks the provenance registry, do you have this exact hash recorded? If there's a match, we know this file is bit for bit identical to the one that was originally attested. All the cryptography and blockchain lookups stay under the hood. The user only sees a simple trusted indicator. When you manage trustable systems, change is as important as the initial attestation. A forward hash chain lets you link versions together. Each new version commits to the hash of the previous one, so you can always prove the exact lineage and detect any missing or rewritten step. Equally crucial is revocation. You need a way to say, this model or this key is no longer safe. A negative attestation on-chain acts like a kill switch, instantly marking that version as untrustworthy. C2PA gives us a cryptographic nutrition label bundled with media, but it lives in metadata. The moment a platform recompresses, screenshots or strips tags, that label can vanish. The fix is to treat C2PA as the evidence and blockchain as the anchor. You hash the C2PA manifest and register that hash on-chain. Even if the file loses its metadata, anyone can recompute the hash and check against the registry to re-establish provenance. Think of your system's lifetime as spanning 3 phases: today's classical cryptography, the quantum break, and your post-quantum defense. RSA and ECC signatures are the weak link. Shor's algorithm targets them directly. But your hash layer, like HA256, is much more robust against known quantum attacks. That suggests a practical strategy. Prioritize anchoring critical data via strong hashes now. Then design your architecture so signature schemes can be swapped or upgraded later with minimal disruption. As you design in this post-AI, post-quantum world, keep one mental loop: hash it, sign it, anchor it. Assume every claim will be challenged later. Make evidence cheap to verify and expensive to fake. Audit ready by default isn't a feature anymore, it's how you manufacture digital truth.